So now we are starting with minimum spanning tree. Okay, so I'll tell you more about it, but when we talk about minimum spanning tree, this is an optimization problem. Okay, what is an optimization problem? An optimization problem is a problem where given an input, given some input, we try to find out certain solution which is either minimizing a certain value or maximizing it. Okay, either maximizing or minimizing. So this is an optimization problem. So when we find the optimal solution, we say this is a solution to the problem, not the solution, because there can be multiple solutions which can achieve that optimal value. Okay, there cannot be more than one minimum or maximum, but there can be a combination of solutions which can reach to that minimum, multiple combinations. Such like I tell you that if I have like 200 books and I want to find out, you combine the books such a way that different sets which can be the minimum. So multiple books, a value I give you like 20. So multiple books can weight up to 20, even their individual weights are different. So this is probably not the best example, but we have very good example here in the form of minimum spanning tree. What is a spanning tree? We need to know. Okay, a spanning tree of a graph is a tree which is connecting every vertex exactly once. Okay, it spans every vertex exactly once, and there is no cycle because that's a tree. Okay, so this is such a tree. Among all the spanning trees, the weight of total weight of each edge is minimum. So what is the weight of an edge? The weight of an edge can be anything, like if you are trying to go from Benton Hall to Armstrong Center, you can have multiple paths connecting, interconnected network of paths which will take you to the destination. And it can be the weight of the path can be defined as the time to cross that path, or maybe the width of the path, or if someone is going by a wheelchair, the difficulty or the accessibility score of that path. Multiple different weight factors can be assigned to an age, and if you sum up those ages and the total weight factor is the minimum, then that's the minimum spanning tree of that particular graph. So here let's see the definition. So the definition says it's an input. Okay, it's an input and output. For every problem you have to have an input and an output. So the input is connected undirected graph. Okay, please remember that the minimum spanning tree is calculated on a connected undirected graph. So given a connected undirected graph G, where with set of vertices V and a set of edges E, with an age weight function. So you have an age weight function. As I said, the age weight is important. Age weight function W, which maps ages to a real number R. Okay, it can be any real number. Maps ages with weights that are real numbers. Okay, so for simplicity, assume all age weights are distinct. Okay, so we assume for this problem that age weights are distinct. So age weights can be same also, but here, just for the simplicity, just to show you simply, we will assume that the age weights are distinct. So what is the output in that case? So this is the input, a graph, a connected weighted graph with age weight function which maps each ages to a certain real number weight. And what is the output? A spanning tree T. So as I said, I defined the spanning tree already. A spanning tree is a tree which connects all the vertices, and that is of minimum weight. So this is a very nice example of a very well constructed problem definition. So the output is a spanning tree of minimum weight. So WT equal to sum of weight of UV. That means it is the sum of each age weight. Okay, so this is not the sum of disordered pair UV. This is the weight function of age UV and the sum of all such ages belonging to the tree T. So that is the weight of the tree. Okay, so then it will be the minimum weight tree once we can minimize this value. So now this type of problem, optimization problem, can be solved with two different procedures, standard procedures. Okay, one is called dynamic programming and the other is called greedy algorithm. Now, what are the differences between dynamic programming and greedy algorithm? I'll talk about it. I'll talk less about dynamic programming because this one will try to solve with greedy algorithm. So, there are some common properties between dynamic programming and greedy algorithm. So, what are the properties? Let's see. So, there is a property called optimal substructure. So, which says optimal solutions to a problem incorporate optimal solutions to related subproblems, which we may solve independently. It might seem a little bit difficult for you to understand. For that, let's try to see a graph. Okay, this is a graph where this is already a tree. Actually, this is assume that this is a MST T. Okay, minimum spanning tree T, considering all these vertices. Now, I am already telling this is a minimum spanning tree. So let's assume there is an edge UV, and I am kind of disconnecting this edge from this graph. Okay, so if I disconnect this edge, what will happen? This part of the graph or the tree will be a subtree T1, and this part of the tree will be a subtree T2. So now the same properties, same algorithms, everything similar thing will be applicable to both, because this will be a subtree of an MST, will also be a subtree, and a subtree, this is another subtree coming out of that MST will also be an MST. So that is the thing. Given a minimum spanning tree, if you remove one edge out of it, then there will be two subtrees formed, and they both of them will be the MSTs of those subgraphs. Okay, part of their so now that is the idea. So optimal solutions to a problem incorporate optimal solutions to related subproblem. So what I'm trying to say, if suppose this is a subgraph, and this is a tree of that graph, there are multiple other vertices, and there are also multiple other vertices, and this is the MST of that subgraph. Now, if we calculate those MST, this MST and this MST of their corresponding subgraphs, and then we connect them using this edge UV, then we will get the MST of this whole graph. Okay, so I'm not showing the other vertices of the graph, so you might feel a little bit confused, but assume there are multiple other vertices, and these are just the MSTs of those graphs. Okay, subgraphs. Then we connect this edge UV, then the whole tree will be the MST of the whole graph G. Okay, so what I'm trying to say, that if we try to solve MSTs of individual subparts of the graph and we combine them, we'll finally get the optimal solutions or the minimum spanning tree for the whole graph. Okay, so this can be solved independently, and they can be connected to make the whole solution. So similar, another thing is the overlapping subproblems. Like when a recursive algorithm revisits the same problem repeatedly, we say that okay, I think I wrote it twice. We say that the optimization problem has overlapping subproblems. Okay, so this is like if I give an algorithmic solution to the minimum spanning tree calculation, and you will see that the same subproblem is coming up and up and up and up. Okay, so like it's called overlapping. Like I try to solve MST for this entire graph, then I have to solve MST for this subgraph and this subgraph, and then again I have to solve within that subgraph maybe MST of this subgraph. So it's a overlapping subproblems. There is a very important difference between this optimization or dynamic programming, greedy algorithm kind of problems, and the divide and conquer type problems. Suppose a divide and conquer is like a merge sort. Okay, merge sort, when you do merge sort, have an array of numbers which you divide, and this will be two different subproblems. They can be of equal size, and what I'm trying to say, that they are not overlapping. Okay, this set of numbers, I mean, they can have repetitions, but this is one part of the array going to one subproblem, another part of the array is going to another problem. So divide and conquer type of problem have independent subproblems. Okay, non-overlapping subproblems, okay, or independent non-overlapping subproblems. This is very important for job interviews and stuff. So, but these problems are overlapping subproblems which we are trying to solve in optimization problem using dynamic programming or greedy type of algorithm. Okay, So this is a very important thing. I have shown you how the problems overlap. You solve one part, and then within that you solve another part. In that way it's possible. Okay, so like these two properties are always there for dynamic programming as well as greedy type of solutions, optimal substructure and overlapping subproblems. Now there is one more property which is very specific to the greedy choice, greedy type of algorithm. It's called a greedy choice property. Okay, so it's a very simple statement. It says that a locally optimal solution choice is globally optimal. What does it mean? Yeah, I will show you an example what it means. But this is a simple idea, is that if at every stage, every day I kind of save some money, or I take optimal number of steps, minimal number of steps over the whole month, I have actually taken minimum number of steps. It's something like that. If every day we do something which is minimal, or every step we do something which is minimal in the whole day, then over a certain period of time, that will also be minimal over that whole period of time. Okay, so that is the basic idea. Let's see this with an example. Suppose there is a big graph, large graph, and we have a minimum spanning tree algorithm which is proposed by Prim. Okay, so Prim's algorithm it's called, and the idea is that maintain a set V minus A as a priority queue. Okay, V minus A is a priority queue. What is the meaning of a priority queue here? We already know about priority queue. It's a queue where the items are prioritized based on certain key value. So like here, suppose the weight is a key value. Key each vertex in Q with the weight of the least weight edge, connecting it to a vertex in A. Suppose this is a graph. Suppose there are two sets. Okay, it's a set A and a set V minus A. Now set A is initially null set. Okay, so now you assume that suppose this is a starting vertex and this is the set A. Okay, so I make this set A, and all the remaining vertices are going to the set V minus A, and they are ordered in a as a priority queue, keyed by their weight, connecting them to the other edges. So let's see now here. So this is A and this is V minus A. Now at the first step, this is a greedy algorithm. So what I do, I find all the vertices which are connected, all the edges going out of this set A, and then so this is like, it's called a cut. And from among this, suppose there were 2-3 different edges going out, and we choose the minimum one, and then whatever vertex is this minimum edge connecting, minimum weight edge is connecting, we include that and make the set A bigger. Okay, set A is now these two vertices. Okay, so now at the next stage, so set V minus A will have one vertex less. So now at the next stage, we see that this is one edge, this is one edge, and this is one edge going out of the set A. Okay, among them we choose the minimum weight edge. So that is the idea of this priority queue. Okay, they will arrange the edges in that way that the minimum weight edge will be in the front, whichever is the minimum. So that is the reason we said here that we want to choose, assume all edge weights are distinct. So because we wanted to make sure the proper prioritization is possible. Okay, if there are all are 5, 5, and 5, the edge weights, is difficult to prioritize them. So better we make it, this is 3 and this is 4 and this is 5. So 3 is smallest. So we go this way. Then this set is increasing and including this one as a into A. So now we will find out all the edges going out of A, and like this one, this one, this one, and this one, and among them we choose the minimum. In this way the set A will grow. You see, every stage we just select one edge, whichever is the minimum weight, going out of the set A and going into set V minus A. So that this is a locally optimal choice, locally optimal among all the edges, the minimum weightage we choose and add it to the set A. In this way, we finally, when the all the vertices will be finished, we'll examine and everyone will come back to A, and the set V minus A will be empty. At that stage, it can be proved that the MST will be formed because at every stage we choose the minimum weightage. Finally all the ages will be, in that order that the minimum weightages are only there. So from this entire graph, it will form a tree. There'll be no cycles, and the MST will be formed. So that's why the Prim's algorithm for forming the minimum spanning tree is a greedy algorithm. Okay, so this is a minimum spanning tree is a greedy algorithm. Okay, remember that. So this is a greedy algorithm optimization problem. So the idea, as I said, at lister connecting to the vertex in A, and I explained this idea. And I also told you what is the difference between divide and conquer type algorithm with the optimization like dynamic programming and greedy type of algorithm. And I explained you the three properties and defined you the minimum spanning tree problem. And now we'll talk more about the Prim's algorithm. We'll see the pseudocode, and we'll see an example, and we'll also see the complexity analysis of Prim's algorithm.